In this example, we have the thin homogeneous bar AB, which is moving in such a way that both A and B are constrained to be moving along guides. Path for A is straight, path for B is curved. We know it starts out from rest in the position that's shown, and what we want to do is find the speed of end A when the bar AB is horizontal. Work energy equation, change in speed, change in position. FBD, we need it to figure out work. So the forces acting on bar AB is going to be a normal force here at A. It's going to be a normal force at B. Surfaces of the guides are smooth, so there's no friction. And there is a weight force of mg. And that's it. So the forces of the three, we can knock out these in terms of work because they're perpendicular to the path of the points at which they act. mg, that does work, but we're going to put that in V. So when we do the work energy equation, what we end up with is the conclusion that the U term is a zero. Let's write down potential for 1. What I'm going to do is put my datum line right here. So the datum is where the bar is at position 2. So the potential for the bar, that's the distance up here to G, is going to be this distance of R. This distance across is R. So what we have here is probably an angle we need to figure out. So I'll call this a theta. And theta, sine theta, is equal to R over L. So that's a known angle. So the potential then for this bar is going to be mg times the height, which is R, this distance here, plus L over 2 times cosine of theta. Like that. V2, that's a 0. V2 is a 0 because it's at the datum line that I chose. T1, a 0. It's initially at rest. T2. In general, I'm going to write this down in terms of the center of mass. So 1/2 mv squared plus 1/2 I omega squared. Like that. And that's it. So therefore, what we have here is the potential at the beginning, mg r plus L over 2 cosine, is equal to the kinetic energy 1/2 mvg squared plus 1/2 ig omega squared. So that's our work energy equation. As usual, we have more unknowns than we have equations. We have 2 unknowns in 1 equation. So we'll use kinematics to get those relationships that we need. If we draw the bar in position 2, that's where we need the relationship between V and omega. B is here, and A is there. So A right before was moving to the left, at least, so it's going to be like this. If I said A, I meant B. A is moving down. If we find the instant center for this bar, we draw perpendicular to VA, perpendicular to VB, so we conclude here that B is the instant center. So since B is the instant center, this implies that the speed of G is equal to L over 2 times omega. And also that VA is equal to L omega. So what we'll have here, let me see if I can do my substitution here. We'll see here that VA is equal to twice VG. Do I want to do that? Let me not do that. Let me just do it as is. So the VG, we'll write that out in our equation. Mg R plus L over 2 cosine is equal to 1/2 mvg, which that's going to be L over 2 omega squared, plus ig omega squared, like this. And this here is 1/12 ml squared. So this becomes 1/3 ml squared. So we have omega for the bar at position 2 is going to be equal to, what, we can cancel out the m's. It's going to be equal to 6g R plus L over 2 cosine divided by L squared, square root, like that. And as we found above, VA then is equal to L omega. So once we know the omega for the bar, we have VA. So a very critical part of this problem really came in step 3. But what led up to that was recognizing we're going to use the work energy equation. Energy is conserved. There's no forces doing non-conservative work. Wrote down V1 and V2. T1 and T2, I chose to write it in terms of G, 1/2 mvg squared plus 1/2 ig omega squared. Got our work energy equation. So as I said, the key part of this is step 3, the kinematics. With that said, the instant center ends up being at B, so therefore VG is L over 2 times omega. We put that back into our work energy equation. We solve for omega, and therefore VA, which is L omega, we have the equation for that.